Welcome to our video on the birth of quantum mechanics, quantization, and the significance of Planck's radiation law and resolving the ultraviolet catastrophe. In the early 20th century, classical physics attempted to predict the distribution of energy among all possible wavelengths emitted by a black body at a specific temperature. According to classical physics, a black body is made up of countless atoms. Each atom vibrates with its own frequency and amplitude, and emit radiation of corresponding frequency. In classical view, the temperature of a black body can vary continuously. It can be adjusted from low to very high values. The energy and frequency of the oscillators primarily depends on the temperature of the black body and increase with temperature continuously. Therefore, the oscillators were considered to emit radiations of all energies and frequencies, leading to the prediction of no upper limit on the energy or intensity of light produced by oscillators vibrating at high frequencies. However, these classical predictions clashed with experimental observations and predicted an infinite energy output at shorter wavelengths, leading to a major problem known as ultraviolet catastrophe. This failure of classical physics to fully explain black body radiation challenged the foundations of the field. Around the year 1900, a brilliant physicist Max Planck proposed a groundbreaking idea. He suggested that the oscillators within the walls of a black body cannot vibrate at a continuous range of frequency, but rather they oscillate at specific frequencies. The values belong to a set of limited values. This radical concept is known as quantization, marked the inception of quantum mechanics. According to Planck's radiation law, the energy of an oscillator is proportional to its frequency. Since frequency of oscillators is quantized, therefore the energy of oscillators is also quantized. The minimum possible value of energy an oscillator can have is hf. This value is called quantum of energy or photon. The higher values of energy are 2hf, 3hf, or integral multiple of hf, where n is called quantum number and represents the state of an oscillator, while h is Planck's constant. An oscillator in high energy state E3 that jumps to a lower energy state E2 will emit a radiation of energy equal to the difference between the two states. An oscillator cannot emit a fraction of its energy but rather emit energy in these discrete quanta. The energy of emitted radiations cannot take continuous values, rather energy is quantized and its values belong to a set of limited allowed values. Planck's radiation law precisely described the intensity of radiation across all wavelengths and temperatures, effectively resolving the ultraviolet catastrophe. It marked the first step towards a quantum understanding of the atomic and subatomic world. Planck's work on black body radiation is strong experimental evidence that light behaves like particle. The energy it carries is compressed in the form of particle and not spread out continuously like a wave. Hope this video was helpful in understanding the Planck's radiation law and birth of quantum mechanics. Thank you for watching.